Today's video is going to be on something called Hess's Law. A pretty simple thing here, actually. So, first of all, the second rule of thermochemistry, you never have to memorize those rules or numbers, but here's what it is telling you. If you have a reaction, okay, so here you have carbon monoxide plus oxygen making carbon dioxide. The enthalpy change, where enthalpy change is the heat change, is negative 283 kilojoules per mole of reaction. So that means that for every mole of CO2 that's made in this reaction, that much heat is released. Remember, that's exothermic. For every mole of CO that's used, that much heat is released. And for every mole of oxygen used, that much heat is released. Well, if we flip the equation around, it is now endothermic the other way. So we have to add heat into this to make it turn into those two things. So whereas heat was being produced or given off when CO2 was made, just the opposite way would be endothermic. We also have doubled the number of moles, so that would double that. So if we were going to get this answer, we'd want to multiply that by 2 and change the sign to positive. So it'd be a positive 566 kilojoules for this reaction. If we go down to Hess's law, so Hess's law, the value of delta H, by enthalpy change for reaction, is the same whether it occurs directly or in a series of steps. Okay, so most reactions, or a lot of reactions, occur in a series of steps, even though a lot of times we just write the overall reaction. Sometimes reactions occur in a series of steps. Like these two things react to make this, that thing goes back into this part and goes through the rest of the reaction. So if we have a reaction that occurs in a series of steps, so we have this reaction comes from these two reactions. All right. First thing we got to do is make sure that these two add up to that. Well, right now we have a mole of carbon on the left-hand side. We want a mole of carbon. And we need to have a mole of CO on the right. So these two reactions added together need to add up to this overall reaction. So these two don't do that. So we a lot of times have to adjust these reactions to make it so we can get this. I'm pretty sure I want to leave the first one this way it is, because I want to use it. I want a mole of carbon on the left-hand side for my overall reaction. I want 1 mole of carbon monoxide on the right-hand side, and right now I have 2 moles on the left-hand side. So I'm going to flip that second equation and divide it in half. Flip it and divide it in half. So if I do that here, I'm just going to kind of write that right here. If I flip it and divide it in half, that's going to make this become 1 mole of CO2 makes 1 mole of CO plus a half a mole of O2. So I just flip this and divided it in half. That means our delta H for that, our enthalpy change, would be flipped. So now instead of being negative, it's now going to be positive. It's going to be endothermic and going to be divided in half. So positive 283 kilojoules. So now these two reactions added together should add up to this. Well, we have a mole of carbon being used. You have 1 mole of oxygen being used and a half mole being produced. The net is that a mole is being used, which is what we want. Notice a mole of CO2 is made in this reaction, and then a mole of CO2 is used in this reaction. So the net is that there's no CO2 in the overall reaction, and a mole of CO is made. So they do add up to that one. Again, it occurs in a series of steps. So carbon reacts with oxygen. So you can't really make this happen. Carbon plus oxygen doesn't make carbon monoxide directly. Carbon plus oxygen makes CO2. That CO2 is made in this reaction, can then decompose into carbon monoxide plus oxygen. So this reaction occurs in a series of steps. The first reaction gives off 393 kilojoules of heat. Second reaction absorbs 283 kilojoules of heat. So the delta H of the overall reaction, we just add those together and gives us the net of that. So negative 393.5 plus 283 gives us negative 110.5. And that's kilojoules per mole or per mole of reaction. Let's go down to the next one. When I put documents up here, sometimes that 7 is supposed to be an arrow, so arrow, arrow, arrow. Sorry, I did not change those in there, but I don't know why that happens. So I'll do that right now. Arrow, arrow, arrow. Here's a priority has arrows. We want to know delta H for the decomposition of 1 mole of acetylene to its elements in their stable state. So our overall reaction is going to be decomposition of C2H2 into its elements, so into carbon and hydrogen, which is diatomic, into carbon plus hydrogen. If we're going to balance that, we need a 2 in front of there. So we want to know what is the enthalpy change for this reaction. Enthalpy change for this, given these reactions. So first of all, we need to make sure these reactions add up to that. Make sure these add up to this one. So at the end, we want a mole of C2H2 on the left-hand side. We've got a mole there, so we probably want to keep that the way it is. So probably not change the top one. We need 2 moles of carbon at the end on the right-hand side. And I don't see carbon anywhere by itself except for right here. So we probably need to flip this one and double it to get to 2 moles of carbon on there. So let's do that. Let's flip it and double it. Change this to blue. So I'm going to flip this and double it. I'm going to put it above it. So we're going to have 2 CO2 forms 2C plus 2O2. So I flipped that and I doubled it. So that's going to change that. That means our delta H is going to be flipped and doubled. So positive 787. So don't use that one. Now we've got to figure out this bottom one. I know I need a mole of H2 on the right-hand side at the end, and I don't think I see H2 anywhere else on there, is there? So we need to flip that bottom one. So let's flip that one. So we're going to have H2O forms H2 plus O2. That means our delta H is going to be positive 285.8 kilojoules. So we'll get rid of that. There's our 3 reactions. Let's make sure those work out. You got a mole of C2H2. 5.5 moles of O2 are being used. That's 2.5 moles of O2. Well, 2 moles are being produced right there. And we have, whoops, this is supposed to be a half right here. That was a half there. It should be a half right there. It looks a little weird. That should be a half. So 2.5 moles of O2 are being produced, 2.5 moles being used. So the O2 cancels out. 2 CO2s are being produced, and 2 CO2s are being used here, so those cancel out. Mole of water is being produced. That mole of water is going to be used down here. Those cancel out. 2 moles of carbon are made, and a mole of H2 is made. So those are the only things left. 3 circled things are the things left. Those are the things we have down there. Now we need to add these together. Add our delta H for that reaction, plus our delta H for that reaction, plus our delta H for that reaction gives us the overall reaction to get this overall reaction. Negative 226.7 kilojoules. All right. There's one more. I'm going to have you guys do it. I will tell you the answer to it. Sorry, I have 7s in there again. So it's giving you those 2 equations. I want you to get to this. The answer there is negative 1776 kilojoules if you get that answer. Try that. People always have a hard time with that. Negative 1776 kilojoules. So try that, see if you can get to that answer.